Hello, spectroscopy. We will discuss about spectroscopy, about IR spectroscopy and Raman spectroscopy. Uh, First, we will start from absorption emission. So, this is a two-level atom. So, there are two levels: ground level and the first level. So, one photon H nu comes in. So from the ground state, it is excited. So it's excited. This is absorption, and after a while, so it is de-excited and emits the photon. So H nu dash. So this is the energy uh, exchange between the photon and the matter. So this is the vibrational spectroscopy. The transition of a vibrational state. So the technique used is to understand the vibration spectroscopy is IR infrared spectroscopy and Raman spectroscopy. Both measure the vibration energy of the chemical bonds in a given sample or given target. So instant light. So this is the energy. Energy is reducing. So this is energy E. This is more energy, and as it goes in this direction, its energy is reducing. If you shine the UV light, so the result in molecule will be electronic transitions, visible and IR vibration in the transition, and IR infrared to microwave, so rotational energy level transition. So there will be different transitions: electronic transition, vibrational transition, rotational transitions. So the bonds in a molecule should be considered, if we consider as a springs, and they obey Hooke's law, Robert Hooke's law, 1660 in England. So the force is equal to minus kx. Uh, F is the restoring force because it's always toward this is moving like this one. So it is moving like this one, and it is coming. The force is bringing it back. It goes like this one. The force is bringing it back. So this is the equilibrium. So the force is always bringing the object toward the center. So K is a spring constant and X is the displacement from the center. So negative sign is the restoring force is always bring the object toward the original position, which is the center equilibrium position. So if it is the spring, so if you give energy to the molecule is excited. So this is excited molecule, and then molecule start vibrating. This is not excitation. This molecule start vibrating. So the molecule has a vibrational modes. So vibrational mode, the standing mode. Standing mode is the mode that is fixed between the two nodes, and there is variation not in the time, variation in the space. So polyatomic molecules, each molecule in the polyatomic molecule, molecule, multi-atom molecule. Each atom, uh, uh, each molecule in the molecule in the big molecule act as a independent mode, normal mode, independent of each other molecules. So if there are n atoms in the molecule, so then there will be a linear and non-linear modes. So if it's a linear mode, so this will be 3n minus 5. And if it is a non-linear mode, so this will be 3n minus 6. Um, so there will be normal modes independent of each other, but has a simultaneously vibration of different parts of the molecule. So vibration and parts of the molecule at the different part will be simultaneously vibrating. So vibrational mode depend upon the atomic mass of the atom, orientation of the atom, and orientation of the bond order, pi bonds and sigma bond, and hydrogen bonding. Uh, how is the hydrogen bonding in the molecule? So normal mode, there are different kind of the modes. So this is symmetric. So this is a one atom, and there are two atoms. So they are both coming up and down simultaneously. This is symmetric vibration. Asymmetric, this is moving slow, and this is moving fast. So asymmetric. So wagging. So this is coming out. Both are coming out like this one. So this is a twist. That means this end is coming slow, and this is faster. So twisting, and that's a scissoring. So they are going on away, inside and outside. And this is a rocking. So the whole set is moving. So whole set is like moving like this one. So out and inside the page. These are the different vibrations. So IR infrared spectroscopy. So this is the design of the spectroscopies of the instrument. This is IR source, infrared source, and this is the laser light is emitted on this one. So this setup of the IR spectroscope. So this is a beam splitter, splitting the beam into two parts. So this is goes on up, and this is down, and this is a mirror, and this is also a mirror, and it is reflected, and this is a sample. This goes to this one, and this is a control. This is the no sample. This is a just empty cavity, same as this one. So this is and then this is a beam splitter, and then it goes to detector, and then it is a processor, and then it is a display. So this, if this is A and this is a B, so here is a detector is acting, and then it is A minus B. So it is extracted. So the molecule in the sample so selectively absorb the incoming energy corresponding to the molecule vibrational mode. So each vibrational mode, so H is a spring, it's gain energy from the IR source, and it start oscillating because of natural frequency. And the transmittance of is recorded. So transmittance is the power out over power in, power irradiance and power input radiation, and this is absorption intensity as a function of frequency. So this is absorption frequency is what the how much the frequency is absorbed in the different in the whole spectrum, and it is displayed, and it is the indication of the absorption of the sample. Absorption A is minus a log of a transmission. So Beer-Lambert law. So this is the log of intensity I initial to initial intensity out is equal to the absorption. It is equal to epsilon, which is absorptivity, fraction of light which is absorbed in the sample. L is the distance traveled by the light in the sample. This is the path length. And C is the concentration, molar concentration. So this is the intensity of the light detected after the traveling the distance L. And this is can be represented by the transmission. T is equal to intensity out over in. This is in over out. That's why it is a negative. So this is equal to exponential of minus mu. Mu is the attenuation coefficient, and d is the distance. So this is so Beer-Lambert law, and this one. So as a CO2, so this is carbon, and this is oxygen. This is oxygen. This is a IR active molecule. IR molecule must have a change in electric dipole moment. Change in dipole moment, this is the polar, that is asymmetric. So one atom moves and generate a net change in the dipole moment. Symmetric, net dipole moment is cancel each other. So this is a polar and a polar. In a polar, net dipole moment is zero. In a polar, asymmetric. So there are polar asymmetric, polar asymmetric, polar symmetric. Polar symmetric, net dipole moment is zero, and polar but asymmetric. So this is dipole moment is existing. So next one is Raman spectroscopy. It depends upon the polarizability of the molecule, and it is a scattering. It represents scattering. Scattering elastically, which is Rayleigh, is very strong. So Rayleigh is the same frequency as the emission. So this one is h nu. So it excites the molecule atom. So then it's de-excited, and it emits the same kind energy h nu. So this is very strong. And second is inelastic scattering, which where the light is shine, so it is excited. So instead of a 0 1, it is go back to some other virtual state. So like this one. So this energy is non-radiative. So that is one to say 0 3. So this is different h nu, smaller h nu dash, which is smaller than this one. So Raman spectrum is the plot of intensity of the Raman photon versus the frequency difference of from the incident light. So incident light, so the how much is the shift from the incident light? So this is the incident light, and then what is the difference? So there's a less energy, and this is higher energy. These are the Stokes, and these are the anti-Stoke lines. So this is the Stokes line. So this is vibration. So this is from ground to this one, and this comes to the any virtual state. So this is a Stokes. This is a loss of energy, and this is a Rayleigh, same energy, and this is from going from the uh, one vibration state to the upper level, and then coming to the more ground state. So this is anti-Stoke, this is gain energy. So this is a loss of energy, less energy, and this is the same energy, and this is a more energy. So this is a symmetric stretch. So symmetric stretch, and this is rocking, and this is scissoring, and this is asymmetric stretch on the Raman side. And on if you complement this one, this is IR absorption of the asymmetric stretch. So the comparison, IR versus Raman. IR is inexpensive, cheaper. Raman is very expensive. This is sensitive to the changes in dipole moment, while this is sensitive to the polarizability. And this shows very well the asymmetric vibrations, and this is showed the symmetric vibration. And this is no good in a liquid. This is good in a liquid as well as others, or any phase of the molecule. So both are the complementary technique. So one is useful for the asymmetric, another one is useful for the symmetric vibration. So this is about the Raman spectroscopy.